Hi, I'm Lauren, and the problem I'm going to be doing is number 51. Two train whistles have identical frequencies of 180 Hz. When one train is at rest in a station sounding its whistle, a beat frequency of 2 Hz is heard from a moving train. What two possible speeds and directions can the moving train have? So first I drew a diagram. So on the left is the station. It has a train in it and it's blowing its whistle. It's at rest. And it is the source. And then on its right, we have this other train that's also blowing its whistle. Both of them are 180 Hertz if you were to stand right in front of the whistle, per se. And the train on the right is going to be of the observer because we're measuring from the moving train. And there's two possible scenarios. The first scenario is that the observer train, the moving train, is moving towards the station. The other scenario is that the moving train is moving away from the station. So I broke it up into two scenarios. First, if the observer train is moving towards the source. So here, because we have beat frequencies, we're going to be using the beat frequency formula of the frequency of the beat equals the frequency of something minus the frequency of another thing. And we know through the Doppler effect that even though, isolated, they're both the station whistle and the observer, moving train whistle have 180 Hertz. When they move relative to each other, from the observer standpoint, the frequencies are going to change. So if the observer is moving towards the source, because it's moving closer and closer as the Doppler effect, the frequency of the station, of the source, is going to be greater than 180 Hertz, or at least it's going to be perceived greater than 180 Hertz to the moving observer. So here we use the beat frequency formula, and we found that 2 Hertz plus the frequency of the observer equals the frequency of the source, meaning that the frequency of the source has to be greater than the observer, and by 2 Hertz. So the frequency of the source would be 182 Hertz. But now going down, so the opposite scenario, what if the observer train is moving away from the source? That would mean that the frequency of the station would be perceived less because you're moving away, and it's 2 Hertz less. So the frequency of the source in that case scenario would be 178 Hertz. So now, you break it up into two scenarios using those two different frequency of source numbers. And we use the Doppler effect formula. So if the observer is moving toward the source would mean that the frequency is 182 Hertz. We plug it into the formula. The frequency of the observer equals the frequency of the source, which is 182 Hertz, times 343 meters per second, which is the relative speed of sound, plus because the observer is moving towards the source, the velocity of the observer over 343 meters per second. And because the station is not moving, we don't have to add any velocity. And so when you isolate the variable, we find that 3.79 meters per second towards the station, that's what the train is moving in that case scenario. But in the second case scenario, if the observer is moving away from the source, we know that the source, the frequency of the source is 178 Hertz. We plug in the same formula, the frequency of the observer, which is always 180 Hertz, equals the frequency of the source, which is 178 Hertz, times 343 meters per second, minus, because now the observer is moving away, the velocity of the observer over 343 meters per second. Again, it's just that because the station is stagnant, and we get that the velocity of the observer equals 3.88 meters per second. You're going to get a negative, but all that means is direction, so it's away from the station. So we have two possible cases and scenarios in both directions.